Hey, on Wednesday after class, if you want, you can go over to A300 in the, which is right beside the cafeteria there, um, in the academic building. And um, in the fall, we always have this celebration called Algebra Day. So it's designed for you guys, people who are taking algebra. And so there's lots of activities that go on there, but in particular, there's food. So I told them to, it starts at 11:30, but I told them to hold back some pizza so that when we get there, we'll still have pizza. So if you want to go after class on Wednesday, you can go get some pizza. And I'm going to be playing, it doesn't say it there. There's lots of games, but I'm playing Wheel of Algebra at that time, so you can come play Wheel of Algebra with me. It's like Wheel of Fortune, except it involves algebra, obviously. And there's some prizes, too, for that game. And also there's like a raffle drawing that goes on, too. So you can participate in that. There's other games as well that are fun going on. So if you want to come after class on Wednesday, because I'm going right after class on Wednesday. Again in A300. I'll mention again on Wednesday. What is that? Oh, okay. I thought that said December 16th. I put some new homeworks up, but the most pressing thing is the homework that's due like today, right? There's a one due on the 14th, which is today, right? So we need to finish that one, try to finish that one, hopefully, or get far into that. I didn't look and see how many people had started on it or how far y'all had gotten into it. So we want to try to, after the lecture today, get as much of that done as we can. So that'll be out of the way before midnight. We have a pretty regular schedule there coming up, okay, of homeworks all the way to the end of the semester. So you're going to have due dates frequently here, or maybe a little bit more frequently than we have in the past, up through the end of the semester. So be paying attention to your list of homeworks and the due dates on those, so you don't let anything slip by just because you weren't paying attention to it. All right, so do you guys have any questions? Taylor's here, so she will. There's really nothing to pass out to most people, but if there's anything I need to give you, Taylor will give it to you when she comes back. Do y'all have questions about anything in particular? Questions? Okay. All right. So I'm going to launch into the lecture. There's a few things that I need to tell you about for this homework. Okay. So we've gotten things a little bit out of order, so I want to make sure that I have discussed everything that's necessary for that homework that's due that's due tonight. Okay, most stuff we've talked about, but there may be one or two things there that we didn't talk about. After the lecture, if they need an iPad, will you get an iPad for them? Okay. Okay, so let's switch to the notes here. There are a lot of problems like this, or variations on this in the homework, not just in the one that's due tonight, but throughout this chapter 2. And we didn't do this example, so I wanted to make sure that I went back and did this example. This is a description of this example describes a linear function, okay? And so it's really just a question about linear functions, but you have to read carefully there to understand. How to set up the linear function that's really described here in the problem. And again, there's lots of problems in the homework that look a lot like this one. So this one says the number of consumer products that use nanotechnology. So nanotechnology are these very small or microscopic machines, okay? Sometimes they're really not machines. They're more like materials, okay, that are engineered at a very small scale, all right? This is kind of a fanciful picture of microtechnology. That looks like some sort of microscopic device that's editing a gene, because that looks like a DNA strand, right? Okay. I don't think things are quite that advanced yet in nanotechnology, so this is kind of a little bit of a scientific fiction picture there. But at any rate, it's certainly a field that's growing. And so it says in 2005, there were only 50 consumer products that use nanotechnology, but that number had grown a lot, okay? By 2015, there were 3,000 such products, okay? And so we're going to assume that growth is steady, okay? Or in other words, we can model the growth of this nanotechnology in consumer products by a linear function. So that's what's given to just immediately in the first question here. It says, use a linear function to predict the number of consumer products that will be using nanotechnology in 2020, next year, okay, based on this information about the past, right? Assuming that, again, this growth is linear, all right? And that's a really important assumption because it's quite possible that that growth is not linear, okay? But since we really have only been working a lot here in the class with linear functions, we're not going to get very far with this question, right? Unless we make that assumption. So we're going to assume here that that growth is linear. So to predict in the future, 2020, right, what we're going to have to do is write down a formula for this linear function. I guess we can make a graph of this linear function too, okay? But really now we're just as capable of writing down formulas for linear functions as we are for drawing graphs for linear functions, right? Okay, as long as we have the correct information. And what do you need to write down the formula for a linear function? What do you need to know to do that? What? Yeah, you need coordinates of what there, Arthur? Yeah, so you need x and y coordinates, right? Okay, how many of those do you need? Two, right? Okay, so you need a couple of them, and so and because we're going to use that to compute the slope, right? Okay, which is going to be a key part of the formula. Arthur, of course, we're not explicitly given points on this linear function, but are we implicitly, right, given coordinates? Yeah. So how can we take the information that we're given there and write that down as coordinates for points? I think turn that around though, okay? Because we're trying to make predictions about the number of products, right? Okay, and that would be based on the year, right? So the year here is going to be the input. Okay, the year is going to be the input because that's the number that we would start with, and then the output, the number that we're trying to predict, is the number of products, right? So the y-axis would be number of consumer products, and the x-axis would be time, right, in years, all right? I guess we could use the last years if we wanted to, but we may be able to go ahead and just use calendar years, right? Okay, so let's try that. So Arthur, tell me those points, right, that we know here based on what we're given. Yeah, right. Sure, that's easy, right? 2005 and 50. Okay, and then what? 2015. Yeah, and 2015, and then 3,000. So I guess what I didn't write down explicitly, but I should, I guess, is it's sort of implied because I already filled in these coordinates, right, for these points, is x is going to be the calendar year, right? Because that's where that's the value that we're filling in for these x coordinates here. is calendar year. And Y there then is going to be the number of nanotechnology products, right? It's actually consumer nanotechnology products. That's a big word to spell. When you use that prefix nano, usually in any sort of context, that usually means today. That usually means small. Okay, very small. We'd have to look up where that prefix comes from, so why that term is used. Okay. All right. So so now we're in good shape, right, for writing down that formula, because now we can calculate the slope. So let's see what the slope turns out to be. So we just apply our slope formula, correct? So we're just going to take the difference in the y coordinates, right? That's the rise. So I'll take 3,000 minus 50, and then divide that by the difference in the x coordinates. That's my run, correct, right? And so I get something like 2950 there, right, divided by 10. And so that is a very convenient slope there. That's 295, right, which is positive. So that, of course, that means that that line is going to be going uphill from left to right, right? That line is going to be increasing because we have positive slope. Well, that's obvious, right? Okay, that line connects these 2 points, so that line has to be increasing, right? So, so what's that? If we had to interpret that slope, what would be our description of what that slope means? So, what's that slope telling us? It's the rate of change, right? So in this context, Arthur, how would you interpret that rate of change?
For every 1 year, 295, what is it, consumer product using nanotechnology?
Something like that, okay, right? Something like that, but we've got to get it ironed out correctly, all right? Something like that won't quite cut it, right? Okay. So what's changing here? What's the y value? What's the y value? Yeah, that's that. So that number of nanotechnology products, right? And so what's happening to that? It's increasing, right? Okay, because this slope is positive, right? So it's increasing, right? And that slope is telling you a rate of change, right? So it's increasing by 295, correct? What? Products, right? Okay. And then how do we turn this into a rate of change? So what do we add here? What phrase do we add there at the end? Yearly, right? Or so you could say yearly, right? Or per year, right? Or each year, right? Lots of different ways you can express the fact, right, that that number of products is going up, right, 295 each year. So, and that rate there is really important. So, you know, if you don't have that in your interpretation of a slope, you know, you're going to get that counted off, right? Okay, you have to have that. So, so when I ask students often to interpret slope, which I do frequently, that's their favorite mistake. They like to leave off that per year or yearly, but that's important because slope is a rate of change, okay? And it's like a speed is a rate of change, right? When you're describing how fast your car is going, you might say, oh, I'm traveling 40 miles per hour, right? Per hour, right? Okay? Same thing here, okay? That number of consumer products is increasing 295 per year, right? Okay? All right, so so we're not finished with the actual problem. This was just a digression there. What we now want to do is write down the formula, correct, okay, for that line. So this is the easy part, correct, because we know the slope, right, and we have points that are on the line, so we can use the point slope formula to just very quickly write down the formula for that line, right? So you've got to remember that point-slope formula, right? Remember, it's y is equal to the slope, right, m. So there's 295. And then what do we put in the parentheses here? X, right? And then what? X minus x1. So, right, so you're going to choose one of your points, right? Okay, and use its y coordinate. So I guess we could use the first point. Doesn't really matter there. Any point will do. So x minus 2005, and then what goes on at the end here? So this is the x1, right? So the y1, right, which is what here, Uni? 50, right, okay. So just add on there that y coordinate for that same point, which in this case is 50. So there it is. There's the formula for that line. And once you've got the formula for that line written down right, then it's easy to use that to make predictions about 2020, for instance, right, okay, if that's what we want to know, okay. So let's do that, right? Is that what we were trying to do here? Make predictions about 2020. So just fill in here 2020, right, for x, and simplify that formula. So what you get there, of course, is easy. That's 295 times 15, right? Because 2020 is 15 years after 2005, and that number of nano products was increasing, we assumed, by 295 per year, right? So we're going to get 15 times 295, right? That increase, correct, from how many there were in 2005, right? Which, remember, was 50. So you're going to take that 295 times 15, right, and just add that on to 50, okay? So what does that turn out to be? Can y'all do those calculations for me? I don't have a calculator here. 4,000 what? 475? Okay, right. So there's our prediction for next year, for 2020. Okay. Let's see. Let's use that same linear function now, since we went to all the trouble to create it, right? This one. We want to use that now to determine how many, how long it's going to take for this number of, to reach 5,000. Okay. Well, that's pretty easy, right? We know it's going to be coming up pretty quick, because already in 2020 it was 4475, right? Okay. But how would we exactly there determine how long it's going to take, or when this number of products will reach 5,000? How do we use the formula to do that? We can sort of guess at that, right? But how can we use our formula to answer that more methodically? Put it in for y, sure, right, okay. This is a number, this 5,000 is a number of products, right? We're calling that y in the problem, so just take that 5,000 and plug it in for y, right, okay, in the equation. So we get this equation to solve. Oops, not quite that equation. This equation, 295 times x minus the 2005 plus the 50. So that should be a fairly easy equation to solve, because we just have x raised to the, there we just have x raised to the first power, right? So I think we can just solve that by using some pretty simple, some pretty simple algebra. So now in lots of the problems where we're dealing with linear functions, or applications of linear functions, we're going to end up solving equations, sometimes more complicated than this one. So I do have to here momentarily, but not immediately, I have to momentarily go back and give us a little bit of review of solving equations, okay? So we've been solving equations really since right from the beginning of the class, right, okay? But the types of equations we're going to solve, or the level of difficulty, is getting ready to intensify. So I want to go back and make sure that we understand how to solve simple equations like this one before we start dealing with some more complicated equations here pretty quickly, all right? But let's go ahead and solve this one. So all you have to do is just simplify both sides, okay? So, and you know simplify, right? That just means carry out the arithmetic by hand. So I'm going to multiply that 295 times the x minus the 2005, all right? So that's going to give me 295x, and then I need my calculator here, right, to help me with this product. So, that's going to give me a big a number, right? What's 2005 times 295? So 591,475. Did I write that down right? And then don't forget, we've got this. It's kind of measly at this point, but because it's right beside that big number. But we still have to add in that 50. Okay, so the 50 hasn't gone anywhere, right? Okay, so let's go ahead and add that in. That's part of the simplifying. So I have 5,000 here is 295x, and then minus this huge product here, 591,475. Oops, but I added 50 to it. So let's go ahead and add in that 50. So when you add in the 50, right, that's going to be 591,525. Am I right? Okay. So there we've got both sides simplified. You can't do any more arithmetic by hand on the right-hand side, okay? All right, so left-hand side is simplified. That's just the number 5,000, so that's simplified. The right-hand side is simplified now, okay? So I simplified both sides. Now what? Next, obviously. Well, the whole process here is solving for x, okay? So this is just one step in solving for x. So what's the next step there in solving for x? Yeah, sure, you got to add to both sides, right? So you're just going to add this gigantic constant here, 591,525, right, to both sides. So we get there 295x is equal to whatever this sum is. So what is that? 596,525, right? That's easy enough. We can just do it in our heads. And now we're just one step away, right? Because to isolate the x, what do I do? What? Wait, say that again. What? Division, right, yeah. Okay, please don't don't subtract the 295 from both sides, right, okay? So don't get in such a big hurry, right, that you make a silly algebraic mistake like that, right? The 295 is multiplied by the x, so you're going to have to divide both sides by 295. But I see that mistake all the time, even in advanced classes, okay? People just are not paying attention, and they'll subtract 295 from both sides, and that's not going to help in this case. So let's see, so approximately there, what is our value for x? So we're probably going to end up with an ugly decimal, but we can round off a little bit. What? So 2021, what? 0.77, okay, which we can round off a little bit further, I guess, to, since this is a calendar year, right, to 2022, right, okay? So it's going to be a couple of more years, right, 2022, before that number of nanotechnology products hits 5,000, correct, okay? But that's assuming that the growth is steady, okay? Assuming that a linear function describes this models or fits this particular situation. Okay, that may not be a correct assumption, by the way. That's kind of a big assumption. So it may turn out that our estimate there is wildly incorrect. Okay, because of that assumption. All right. So again, you're going to see lots of examples like this one in several examples like this in the homework where they're asking you different things about linear functions, and they're just giving you a description of linear function from some sort of, in some sort of context like this one. There's one other type of problem that's mentioned in the homework that has to do with the important property of straight lines. So I want to show you this, okay? Because this comes up in lots of different applications in advanced classes, your pre-calculus class, or if you go to take a calculus. So if you have two lines, okay, right? Those lines are said to be parallel to each other if they do not intersect, okay? So I've tried to draw these two lines as parallel. They look like they're not quite parallel, but they're supposed to be parallel, okay? So those two lines there are supposed to be parallel. And perpendicular lines are lines that do intersect, but they cross each other at a 90-degree angle, a right angle, okay? And so we're frequently in your pre-calculus class or in calculus class, you are frequently encountering parallel, especially parallel lines, okay, but sometimes also perpendicular lines. And there's a famous relationship between the slopes of parallel and perpendicular lines. One of them is pretty obvious. For parallel lines, their slopes are the same, okay? So if two lines are parallel to one another, they do not intersect, they're going to have exactly the same slope. And you can prove this pretty easily from geometry. We're not going to show the proof, but it comes from just some basic ideas in geometry. But what's important to us is that if we're given two parallel lines, or we can somehow deduce that two lines are parallel, we will know then that their slopes are identical, or vice versa. If you have two lines and you can tell that their slopes are the same for some reason, then you know when you graph those two lines, they're going to be parallel to each other. That means they're never going to intersect. That kind of makes sense, right? Because the slope, right, sort of gives you geometric information about how a line is oriented, right, when you graph it in the rectangular coordinate system. So if two lines are oriented exactly the same way, in other words, they don't intersect, then they're going to have exactly the same slope, correct? Okay. So you can sort of understand intuitively, right, why parallel lines have the same slope. Now, there's also a relationship, though, which is not as easy to understand, okay? But this is true, and you can also prove it from geometry. It takes a little bit more work, though. If you have two lines that are perpendicular, that is, they meet at a 90-degree angle, okay? So they cross each other exactly at a 90-degree angle. There's also a relationship between the slopes of perpendicular lines. And the relationship is the slopes are sort of opposite of one another. By opposite, in this case, we mean the slopes are negative reciprocals of each other, okay? So, so if these two lines have slope m, whatever that value m is, looks like it's going to be positive, right? But if these two lines have slope m, then if we draw a perpendicular line to either of these two lines, its slope is going to be the negative reciprocal. So you take the reciprocal of this slope, right? You just invert it, but you have to change the sign, okay? And that will give you the slope of the perpendicular line. And again, sometimes that information is useful because sometimes in practice we're going to encounter lines that we know are parallel for some reason, or we know are perpendicular for some reason, and it's helpful to know the relationship between the slopes of those parallel or perpendicular lines. Let's just apply this knowledge to just a very simple problem here. So we want to write down the formula for the line that's parallel to the line parallel, right? So it doesn't intersect with this line, 2x plus 5, and this parallel line is going to pass through the point minus 2, 5, okay? So notice I'm giving here a completely verbal description of what's kind of a geometric situation here, but we're not going to try to draw the picture. So I want to write down a formula for a line that's not the same as this line, but parallel to this line. So parallel to this line. But this new line that I'm writing down passes through this point, minus 2 and 5. Okay. By the way, it may turn out that this is kind of a bogus problem, because it could be that this line passes through this point. Okay. If this line passes through this point, then this problem, in a way, doesn't make sense. Okay. How can we check that to see if this given line passes through this point? By doing what? Yeah, plug in the coordinates, right? So just do substitution and see what happens. So let's try that first to make sure that this problem even makes sense. So if I plug in the coordinates into this given line, so I'm going to plug 5 in for y and minus 2 in for x, and I have to check then to see if that equation is true. Is that equation true? I don't think so, right? Because that says 5 is equal to, this is minus 4 plus 5, which is 1, right? Well, 5 does not equal 1, correct? Okay, so that's a false equation, and so this line does not pass through this point. But so what I'm looking for is kind of the next best thing. I want a line that does pass through this point, but it can't be this line, but I want it parallel to this one, okay? So it's going to have the same slope, right, because they're parallel, but I want it to pass through this point, okay? So this is really easy, correct? Because I have a point, right, that my parallel line passes through. And do I know the slope of the parallel line now? It's 2, right, because it has to be the same as the slope of the given line, correct? But that slope is easy to read off, because this line is written down in slope, and what's that number called? Y-intercept. So this line is written down in slope-intercept form, right? I don't care about the y-intercept, but the slope is important to me here, right? I can see that the slope here is 2. Just read that off. So this is just another problem about lines. All problems about lines are really very similar, okay, because lines are very simple functions. That's why they're so popular, okay. They're very easy to use and understand. Essentially what we're being asked here is write down a formula for a line that passes through this point and has this slope. Well, you know, we can do this now kind of in our sleep, right? Okay. What's that formula going to be then? So you just use your point slope formula, correct? So what's that going to be? So y is equal to, how do we write that down now? Right, so it's the slope, right? And then in parentheses, correct, you have x, and then minus the x-coordinate of the point you want the line to pass through. This is just what we did in the prior example, right? But that x-coordinate is minus 2, all right? So ultimately, that's going to end up being x plus 2, correct? Because minus a minus 2 is plus 2. Oh, I do not want you to write this down. Okay? If you write that down, I will punish you in some terrible way, okay? Because remember I warned you about this. You cannot have arithmetic operations written side by side like this, okay? So if you have to write them side by side, you're going to have to separate them with parentheses, all right? So that's why I put the parentheses in here around the minus 2. What goes on the outside then? 5, right, okay? So there we have just plus 5. That's it. Really, you can stop right there. That is the equation for the line. It's not simplified, but that is the equation for the line, okay? That is the answer. Now, if you want to simplify it, you can simplify it in various ways there. Of course, you can write the minus as a plus. So you'd have x plus 2 plus 5. If you want to keep going, you can multiply the 2 times the x plus 2. So you would get 2x plus 4 plus 5, which is 9, right? So you would end up here with 2x plus 9 if you want to simplify it to that level. That is the slope-intercept form, correct? So you know the slope is 2. We already knew that. Here we can also tell the y-intercept is 9, right? So our new line is going to pass through somewhere here up 9 on the y-axis, right? What about perpendicular? So let's ask the same question. So I want a line that's perpendicular to 2x plus 5, but passes through the point minus 2, 5. Okay? So I want a new line that passes through that same point, minus 2, 5, right? But I want it to be perpendicular to, instead of parallel to, 2x plus 5. Okay? But we already know, right? The slope of this line is 2. So what is going to be the slope of the line that we're trying to write down here? So what's the relationship between perpendicular slopes? Negative reciprocal. So you take the reciprocal of 2. What's the reciprocal of 2? What happens when you invert a 2? Think of 2 as a fraction. How can you write 2 as a fraction? 2 over what? 1, right, okay. Now it's easy to take the reciprocal, right? The reciprocal would be 1 over 2 instead of 2 over 1. So the reciprocal of 2 is 1/2, and then just change the sign, okay? So just make that a minus. So our new line is going to have negative slope, right? Okay, and just passes through that same point. So again, really easy to write that down now, right? We would have y is equal to minus 1/2, that new slope, right? X minus a minus 2, right? And then plus 5. There it is, okay? There is just that easy. That's the equation for the perpendicular line. So kind of the fact you have to remember when you're doing your homework, and then also something that might be good to write down on your survival card for the next test, right, is this relationship, right? Parallel lines have the same slope. Perpendicular lines have negative reciprocal slopes, okay? Their slopes are negative reciprocals of one another. That seems like kind of an obscure fact about straight lines, okay? And in a way it is, but it's an obscure fact that pops up as being useful from time to time, okay? So that's why we take the time to stop and talk about it here, since we're talking about straight lines. Okay. Now, before we left last time, okay, we mentioned this, so let's get a little bit further into this. One type of linear function that again appears frequently in applications is this very simple type of linear function where the y-intercept is 0, okay? You could also have the slope as being 0, okay? Those are called constant functions, remember. Those are also kind of important, but they don't show up as much in applications, all right? But linear functions where the y-intercept is 0, those show up very frequently in applications, especially in science, all right? And so these seems like not even worth mentioning, right? Because it's such a simple type of linear function. But we have to talk about them because you're going to see them frequently in your science courses. And but the other thing is the terminology around these types of functions is a little bit different, okay? Because these linear functions with y-intercept 0, these have been used in science for hundreds of years. So for historical reasons, they've kind of developed a different terminology around these functions. So I have to explain to you a little bit or show you a little bit the terminology. All right. So in science, these linear functions where the y-intercept is 0, these are called direct proportion functions. Direct proportion function. So whenever you hear the term direct proportion function, you'll know, oh, that's just a linear function, a simple linear function where the y-intercept is 0. And in science, the slope is not referred to as the slope, but that's referred to as the constant of proportionality. Okay, and again, this is terminology that just develops historically. Okay, because these direct proportion functions have been used for hundreds of years, and they've been used in lots of disciplines other than mathematics. So these other disciplines like science have sort of created their own terminology around these functions. So often you will see direct proportion functions rather than writing them down as n times x, you'll see them written down as k times x. So we're just going to change the name of the slope there from m to k, and we call it different. Instead of calling it slope, we call that the constant of proportionality. But remember, constant of proportionality just means slope, okay? So when you hear that term in your science class, that means the same as slope, okay? All right. So here's a very typical sort of situation for in using direct proportion functions. All right. So in this problem, we're given that the quantity y is directly proportional to the quantity x. What that means is y is a function of x. Okay. Right? So, but that type of function is a linear function where the y-intercept is 0. Okay? So it's a very simple, y is a very simple function of x. So these so-called direct proportion functions are really easy to use. Okay? And again, in this context, rather than calling the slope, instead we call the slope the constant of proportionality. But that means the same as slope. And usually we label it as k rather than m. All right, so first question there is find the constant of proportionality. This is the same as asking you to find the slope, okay? Now, let's see, what information are we given here, though, about this, direct proportion, about this linear function? We do have a little information here, right? We're told that y is equal to 20 when x is equal to 8. So essentially, what are we given off of this function? When you're told y is 20 when x is 8. Danny, what are we being given there when we're told that y is 20 when x is 8? It's coordinates, right? Those are coordinates of a point, right? Okay. So what is that point? What? 8 and 20, right. Yeah, you can just read that off, Danny, right? Okay, that couldn't be too much difficult, right? Okay? Yeah, okay. All right, so we have there this point. Now, however, remember, when we're asked for the constant of proportionality, right, okay, that means slope, correct? Now, normally when we're looking for the slope, 1 point is not going to do it, right, okay? How many points do we usually really need there? 2, right, okay? We really need a couple of points. But now look, this is where we have to think, okay, about what a direct proportion function really is, okay? Because remember, I told you direct proportion function is a linear function, but it's special in the sense that, what's special about it? The y-intercept is equal to 0, right. So, look, what that tells us, Kevin, is we actually do have another point, okay? Right? We actually do have another point. Because if we know the y-intercept is 0, what's another point that we know is going to be on this, direct proportion function? So it's sort of implied here. We're not given it, but we can sort of understand that it's there. What's that other point? The y-intercept, okay? So the y-intercept is 0. If we know the y-intercept is 0, what's the other point that's got to be on this line? What do y-intercepts look like, Skylar? X equals 0, right, okay? And then the second number is the y-intercept, correct? But what's the y-intercept here? 0, right, okay? Because this is a direct proportion function, all right? So we know there that the y-intercept is going to be 0, okay? So you really do have 2 points there for calculating the slope, all right? Well, that's pretty easy now, right? Okay, so we've got those 2 points there. This is going to be a really easy calculation. I'm not going to use m, though, for the slope. Remember, in the context of direct proportion functions, how you're going to see this in science is that slope is going to be referred to as k. But it means same thing, right? Okay, so what is the slope here? Yeah, pretty easy, right? You're going to have 20 minus 0 over 8 minus 0. Gee, that just turns out to be 20 over 8, right? Okay. If we reduce that, let's see, what's 20 over 8? 2.5 or 5 halves, right? Okay. So there is our constant of proportionality. 5 halves. So k there is equal to 5 halves. All right, let me show you another way we could have discovered that constant of proportionality, though. All right, here's a second way. All right, this is only going to apply, though, in this particular for direct proportion functions. There's a second way you can determine what the slope is, okay? And that has to, and the reason that's the case is because the formula for direct proportion functions is so easy, all right? Remember, the formula for direct proportion functions looks like what? You just have y equals what? Times what? X, right, with no y-intercept, correct, okay? Just with no y-intercept. Look, but you know this direct proportion function has to have y equal 20 when x equals 8, correct? So you can go ahead and plug in y for 20 for y I mean, and 8 for x. And you get this very simple equation, 20 equals k times 8. You can, because you see there's no y-intercept, right? So now you can just solve this equation for k. And of course, you're going to get the same thing, right? Okay, so you get k there is equal to 20 over 8, right? Which, of course, is 5 halves. So there's a second way that we could determine there the slope, right? Or the constant of proportionality. All right. Now, once you know the constant of proportionality, then you know everything really there is to know about this function, because you can now fill that into the formula, and so there it is. Y equals 5 halves times x. That's it. Okay. And now wherever you're asked to actually apply that formula, you've got it, right? So the follow-up to finding the constant proportionality would be questions like this. Find y when x is equal to 25, okay? Or it could be vice versa. Find x when y is some given value. But all of that just comes from knowing the formula. All right, so let's see if we can do this. Remember, that formula was very simple, right? Y is equal to 5 halves times x. So what's y going to be when x is 25? Just plug in 25 for x, right? And then just calculate that matching y value. Let's see. That's going to be 5 times 25, which is 125, divided by 2. If you want to, you can just leave that as 125 divided by 2, all right? If you need to convert that to a decimal, of course, you can do that with your calculator. That's pretty easy, though. What is that, 62.5? I think so, right? Okay. So when x is 25, y is going to be 62.5. Or vice versa, let's see, what's x going to be when y is 32, okay? Exactly the same formula, though, right? Applies. You're just plugging in a different variable. So here we would plug 32 in for y is 5 halves times x. And there we are back with solving an equation. Okay, all right. So as I mentioned, we're going to be running into lots of situations now in these problems for the rest of the course where we're going to be asked to solve equations. So how do I solve this equation? That's almost as simple an equation as one could solve, right? Okay. The only reason I say almost is because instead of being a whole number, this coefficient is 5 halves, right? So that makes it a little bit trickier. So how do we solve that equation for x? So how do we eliminate that coefficient, right, of 5 halves? I needed to get just x, right? I don't want 5 halves x. So what? Yeah, one thing I could do is divide both sides by 5 halves, right? Okay, so that's possible. That's a little bit awkward, though, because, you know, it's kind of awkward sometimes or clumsy sometimes to divide by a fraction, right? You have to think about what it means to divide both sides by a fraction. Arthur, I have a little bit more straightforward way, maybe, okay, of solving this equation. Instead of dividing by 5 halves, which works, okay, that's fine, but is there another way that we could eliminate that 5 halves? Yeah, multiply by, not multiply by 5, I think, but what are you thinking there, Joshua? Oh, I see. So Joshua's going to go in a little bit more roundabout way, right? Okay. He says, oh, I'm going to first, which is good. He said, first, I'm going to multiply both sides by 2, right? Okay. And what's the advantage of doing that, Joshua? Multiplying both sides by 2. Why'd you do that, in other words? What good thing happens here on the right-hand side when you multiply by 2? Yeah, the 2's divide out, right, okay. So you were trying to cancel the 2, correct? So there you can just cancel the 2, all right, and so you get 64 there is equal to 5, and now x, right? And so now it's pretty easy to solve for x. All you have to do is what? Now you divide by 5, right? Okay, so now I'm going to divide both sides by 5. So we get x there is 64 fifths. All right. So that took a couple of extra steps, but in some sense that's a little bit easier, right, than dividing by 5 halves, right? Okay. Just multiply by 2 and then divide by 5. Okay. So you sort of avoided there having to work with fractions, correct? Okay. Multiply by 2, divide by 5. Those are whole numbers. Multiply by 2, divide by 5, right? Okay. And there we arrived at the answer 64 fifths. Now, look, actually, Joshua, those two steps that you went through, multiplying by 2 and dividing by 5, we could have combined those into one step. Let me show you how here. So let's go back to the original equation. See, what you said is I'm going to multiply by 2, right? And then I'm going to divide by 5. But you can do that all at once, okay? I can multiply by 2 and divide by 5 all at the same time, because that is the same as multiplying by 2 fifths. So you could have multiplied both sides by 2 fifths. Notice that 2 fifths is the reciprocal of the 5 halves coefficient on the x. So when you multiply both sides by 2 fifths, the 2's divide out and the 5's also divide out, and you get left with on the right-hand side there just plain x, okay? Now, you still have to multiply the 2 fifths on the left-hand side, and that, again, of course, is going to work out to be 64 fifths, okay? 2 times 32 is 64 divided by 5, right? So you get 64 fifths there. So there you have 3 options, right, for solving that equation. You can just divide by the coefficient, or you can take this 2-step process of dividing out the multiplying out the 2 and then dividing out the 5, or you can do that all at once, multiply both sides by 2 fifths, the reciprocal of the 5 halves. That will give you just x, and then whatever you get on the left-hand side, okay? So lots of ways to sort of skin that cat, right? Lots of ways to solve that equation, all right? All of them are correct as long as you carry out the arithmetic correctly, right? Okay? So as long as you're patient, right, and follow steps that are allowable, you should be able to solve a simple equation like that one. All right, now, I told you, right, that these direct proportion functions come up in science a lot. Here's a famous example of a direct proportion function, okay? You cannot do mechanical engineering without this direct proportion function, okay? So for those of you who are interested in mechanical engineering, this is a very important foundational fact in mechanical engineering here, all right, also in physics. All right, so here's how this direct proportion works. The distance that a spring stretches, okay, is directly proportional to the weight attached to the spring, okay, right? So that in a part of that is kind of intuitively obvious, right? Okay. So I've drawn a very crude picture here. If you have a spring, right, and you attach a weight, right, to the spring, of course, that's going to stretch the spring, okay? But the key thing is how far is that string going to stretch, right? Okay, that's what we want to know, and this is what this direct proportion function tells you, okay? The amount of stretch of the spring is directly proportional to the weight attached to the spring, okay? So this is called Hooke's law. This has a name, all right? That's how important this fact is, okay? So it's a good thing for engineering purposes that there's such a simple relationship, okay, a direct proportion relationship between how far a string stretches when you attach a weight to it, okay? Because if this were a complicated function, wow, it would make our life a lot more difficult, all right? But it turns out to be a simple linear function. In fact, just a direct proportion function. Okay. Now, how far that string stretches depends on, of course, how heavy that spring is, right? So if you have a thick, heavy spring, it's not going to stretch as far, right, as you have some simple spring made out of a light material. So in this particular example, the spring that we're dealing with is going to stretch 8 inches, okay, 8 inches, when the weight attached is 15 pounds, okay, all right? And here's what we want to find. What's the constant of proportionality, right, for this particular spring? By the way, that's called, in this context, that is called the spring constant. So that's what we're getting ready to determine here. What's the constant for this particular spring? And then once you know what that spring constant is, you kind of know the behavior of this spring, right? Because you can determine how far it's going to stretch for any sort of weight that's attached to it, okay? All right, so how do we find that spring constant from the information that we're given? Key fact, right? This is a direct proportion function. That you have to know. So that is what Robert Hooke, the British physicist, discovered for us, okay? That this relationship is a direct proportion function, all right? I don't know how Hooke came to that conclusion, all right? Okay, but he did at some point, and his name is attached to it. Because this is, again, a proportion function that comes up constantly in engineering applications, also in physics as well, all right? Not that we're stretching springs all that often, okay, all right? But many systems can be understood as sort of attaching weights to springs, okay? Even if you don't have, an actual spring with a weight attached to it. All right. Okay, so how do we determine the spring constant here? Same as the constant of proportionality. So what's the really important thing that we want to write down? Y equals what? Emiliano, what? That's it, okay? That's the key thing that you want to write down. Remember, that just tells us that this function that relates that weight to that stretch of that spring is a direct proportion function. We were told that, right? Okay, but there's how we express that mathematically. And once you write that down mathematically, then really everything else flows from that, okay? Now, to determine the spring constant, right, you just plug in values that you're given, okay? So we, No, y is going to be 8, right, when x is, 15, right? So what's k? Doesn't take much to solve that equation, what? 8/15, right? 8 over 15. So there is our spring constant, okay? 8/15. Again, now that is that spring constant is related to sort of the size of that spring. Different springs are going to have different spring constants, okay? But this spring has a spring constant of 8/15. So now we can fill that into our formula. So we know y is equal to 8/15 times x. And see, once you've got that written down, then all the other questions become really very simple. So how far will the string stretch if we attach a 25-pound weight to it, right? Okay. Obviously, it's going to stretch a little bit further than 8 inches, right? Okay. But how much further will it stretch? Well, all we have to do is just plug in 25 for x, correct? Okay. Because x there represented the weight. So just do a simple calculation here. Let's see, what is that? 8 times 25, 8 times 25 divided by 15. Let's see, we can reduce 25 over 15 though, can't we? Because 5 divides into both of those numbers, right? So if we divide 5 into both of those numbers, we can reduce 25 over 15 to 5 over 3, right? So we end up with 40 over 3, which if you want to write that as a decimal, right, maybe easier to understand, that's 13.33, I think, right? Okay. So if you attach a 25-pound weight to this particular spring, it's going to stretch out, instead of 8 inches, right, it'll stretch out 13.3 inches. Let's see if we can do that backwards. So suppose we attach a weight to a spring, and we stretch the spring there by 3.2 inches. Okay, and then we want to know how heavy is that object. Wow, this sounds kind of familiar, right? Okay, because notice here we are using that spring. We're going to use that spring to determine the weight of the object attached to it. That sounds like a familiar device. What does that sound like? So you attach an object to a spring, and you look at how far the spring stretches, and then from that information you determine the weight of the object. What does that sound like? A scale, that's exactly what that is, okay, right, okay. That is a scale, okay. That's how scales work, all right, yeah. Okay, at least mechanical scales, correct, okay. Mechanical scales are based on springs, right, okay, right. And for a mechanical scale built on a spring, we're going to know what the spring constant is, okay. So when we put something on that scale, right, okay, it's going to stretch that spring, correct, okay, but we'll know the spring constant because we built the scale, right, and so based on how far that spring stretches, we're going to know what the weight of that object is, right? That's exactly how scales work, right, okay? So what this problem is describing is a scale, but scales depend on Hooke's law, but Hooke's law is a direct proportion function, okay? All right, so let's see. Well, let's answer this one really quickly. So I know what my direct proportion function is, right? It's 8/15 times, was that right? 8/15 times x, and I'm plugging in 3.2 for y, right? Because I do not know the x. I do not know the weight, but I know the distance that the spring is stretching, right? So now I have to solve that equation. So we just solved an equation like that one 3 different ways, right, in the prior example. So what's a fast way of solving that? What now? Multiply both sides by 15 over 8, right, which is the same as first multiplying by 15, right, to divide out the 15s, and then dividing out the 8s, right? So the 15s divide out and the 8s divide out, and we get 8. X is equal to whatever 15 over 8 times 3.2 is. Okay, so our calculator will help us with that. Let's see, 15 times 3.2, I think, is 48 divided by 8, and that's easy. That is 6. All right, so. That was 6 pounds, right? Okay. That was how much was attached to our spring, right? Was a 6-pound weight. Okay. All right. So what we're going to look at next, but not today, is lots of examples. Since we've been practiced a little bit there in those examples with solving equations, okay? Next time we're going to start by solving a bunch of equations, okay? Again, just to review simple techniques for solving equations before we start encountering equations that are maybe a lot more difficult to solve, okay? All right, we're going to stop there, okay? All right. So our goal for today now is to